because that's tangent to that line at that point. And right here it would be in that direction. So it's always going to be tangent to the electric field vector at any point in space. The second thing is that the spacing of the lines tells you about the electric field. Close spacing, that means that it's a strong field. And far spacing means that it's a weak field. So here, really close to the charges, you can see the lines are very close together. That's going to be strong field. And out here, where the lines are much further apart, the field is going to be weak. Okay. The third thing is that field lines never cross. As you can get them to cross, you break physics. And the fourth thing is that they start at positive and they end at negative. Okay, so that's how you draw field lines. They start from the positive, they end at the negative, they're continuous lines, they're in the direction of E, and the spacing of them tells you about the strength of the field. Okay, let's go ahead and take a 5-minute break, and we will get back to it.
That's my favorite.
All my roommates used to sushi.
Oh. Okay, well, next time I'll like set this up beforehand so I know where I'm gonna record from. I can like see how it views. I want to like find a way to attach like to like projectors and stuff where the frame hits like it's like a bar or
Yeah.
like
That's one. GoPros are awesome, but that's one thing that's like you got to guess where they're.
Yeah,
but they have a big field of view, so
Yeah.
that part's cool.
like I guess I'll see when your harmonic necessarily when I'm editing it if it would have seen it all from the middle or not.
Right. I would like to get a GoPro at some point.
It's from the library for free. The library just checks them out to us.
There's also media services that check out different cameras and stuff. Like after the exam, I'm going to do video solutions for the exam. I need to get a camera for that. I would use my phone, but it has like 0 space.
That's why I got last quarter I would do this for all my different speeches that I had to do for Comp 102.
What is this over here, though? The lounge? Yeah, I like it.
I'm not going to edit out this very
Don't.
What's in the satchel?
Who brought donuts? Some poor soul is going to be watching this video. It's like somebody actually brought donuts.
Right?
I usually bring pizzas to the midterms.
You do?
$+. And this time we only got one class instead of 3. I had to buy 4, so.
I usually just know other people who's got $+. So like upper class. Oh.
Why does everything but me? What?
There's sunglasses under the Oh, just don't want you to step on them.
Yeah.
Okay.
So yeah, I'm gonna like all this handwriting that you can't read, just write over it. So take up the rest of my night before I go to softball.
It's that late?
It's 10:30.
I'm asleep.
And I'll just bring out flashlight tomorrow, give it to him. He'll upload to YouTube, but get it out. I get it right.
And so you make this adjustment and it's like so easy to adjust the height. Yeah, they can get on that one side higher or lower. It makes it easier to get a super lightweight hand. So I do this much credit. Just have I could set it up. Chalkboard. All right. All right, let's get back to it. So, some types of problems from this chapter. This is 26 still. So I could ask you to calculate the electric field vector at a given point. And maybe I ask you for, there's some point charges. Okay, so you have to use the equation for a point charge, or if there's many point charges, you have to use superposition and add up all the electric fields from all the different point charges, and those are like discrete point charges. Or like from a dipole, using some of the dipole equations, or from a plane or two planes. Okay, if I have more than one plane, I could set up a couple of planes and ask you to calculate the electric field in some point in space using superposition. Any of the geometries, right? You get the idea. Okay, and any combination thereof. I could put a plane and a sphere and give you the equation for each of them and say, yeah, okay, what's the electric field at this point in space right here? So that's one thing I could ask you about. And we did some of this mostly with just point charges, finding the electric field in space, but all of these scenarios are valid. Okay, also, you can calculate the E field at a point due to a continuous charge distribution. Okay, and what does that involve? Yeah, that's the integral, right? So in that case, we will break up our, if it's a line charge, you break it up into some little dq pieces that are each dx or dy in length, or maybe arc length, it would be a ds in length, and then you're going to integrate over the whole distribution of charges. And we can talk about that in a minute. So this is something that I might ask you to do. We did this, I did examples of this for a line charge in class. I did examples of this for a disk, for an infinite plane of charge, a ring, I did it for a ring. Those are all examples that I did in class. From our lab, we also did a semicircle of charge, so that's a linear charge density, but in a half circle. And we did a line that was oriented in this direction like that, with a point out there. But we also did this geometry in class. So I would look at all of those, and we can talk about some of those in a second, but I want to also get to the other types of problems from this chapter. I could ask you to derive any of those geometries too, right? That would sort of fall under this category of calculated E field. And then the last thing would be the motion of a particle, a charged particle. In the E field. Now, a lot of the electric fields are not uniform, so I could ask you, given some charge distribution or some electric field that's not uniform, I could ask you to calculate the instantaneous force or the instantaneous acceleration a particle would undergo. But if I'm going to ask you any more complex question about the motion of a charged particle in the E field, it's probably going to be about a uniform electric field. Okay, and in that case, you find the acceleration. Well, first of all, you calculate the force. How do you calculate the force? Yep. F equals Q times E. Okay. Then after you calculate the force, you would find the acceleration. How do you find the acceleration? Yeah. F equals ma. And then from there, you would use kinematics. Which you learned about in 141, to solve whatever the rest of the problem is, like the angle an electron exits a field. And we did one of these on the quiz where you had some charged particle. It was going through some parallel plate capacitors. That's a uniform electric field. And from there, you just had to use this, do the kinematics to figure out what angle it came out. Now that could also work in reverse, right? I could give you some angle or something about the motion of the particle and ask you how strong the field is, right? So it can work in reverse too. Yes?
Those are all, so the four like basic ones, those are all uniform electric fields, right?
No, those are all, none of those. Only one.
So the integrals are?
No, none of those are. The only thing that's a uniform electric field are in between a parallel plate capacitor and an infinite plane of charge. Those are the only two things that cause a uniform electric field. That's a good point, right? Uniform electric field. This right here, infinite plane of charge. Or parallel plates. Those are the only two uniform electric fields. Everything else, right? the electric field decreases as 1 over r squared, or 1 over r, or has some other, like a dipole, has some other non-uniform electric field. So good question, that's a good point. So for this, it will be one of these two geometries if I'm asking you anything about the motion. Otherwise, right, the force is changing at every position in time, and that would be pretty much impossible to calculate, at least, well, it would be some integral, because you would have to add up all of the force. It's a nightmare, so don't do that. I won't do that to you. Okay, so I have some examples of these here that I did in class. I don't know if you guys want me to go over them. It seems like kind of a good use of time, but it also seems like not as good of a use of time, because I feel like you're decent at this, but not as good with Gauss's law. So would you rather have me go over you want me to go over one example of this, or do you want me to skip it and it's setting up those integrals? Who wants me to set up one of these integrals and do it? I could do a simple one, some of you. Okay. Want me to do, I could do it for like a line charge.
I have a question.
Yes.
Is there any way like we could snag some photos of those just to review, or you could post them on Polyline, like just photos of them?
Sure, yeah. Well, a lot of them are worked out in the book.
Oh, are they?
Yeah. So,
that one's cool.
yeah, if you want, all the ones I did in class, those are like the classic examples.
Okay.
Those are all worked out in the book. But if you want me to work out the ones that we did in lab and post those to PolyLearn, I can do that, because those aren't in the book. Okay, I can do that. So let's see here. All right, I'll do one. I'll do the line, the electric field of a line charge, because that one has a lot of the good pieces, but it's not too hard. Okay, I won't ask you to solve any integrals that are too hard. If I want you to solve the integral, I will give you a table of integrals. Okay. So the electric field of a line charge, that was something like this right here. We have some line of charge, and we have some point P out here, and we want to find out what the electric field looks like at point P. Now, we need to break this up into a bunch of little DQs, little pieces of